Sorry that I wasn't able to get any images into you. I wasn't able to get the material that I wanted.
Okay. All right. What else you got for me? What are you going to teach me today? Let me put it like that.
All right. Let's see. Let me just get out the book that I have.
Something you can verbalize, then we'll just do it the regular way we used to do
it. Yes, sir. All right. It's more matrix stuff. How do you feel about that?
It depends on how hard it is.
Okay.
Yeah, it depends on the matrix. There's a lot of levels to all of this math.
All right.
Just so you know, I mean, math tends to go from algebra to calculus, but each level, like there are geometry problems that are level 9 difficulties that you'd have, that would give, college graduates difficulty. So
wow.
Each sublevel, like geometry, trig, precalculus, they all can get really quite hard, and the current education system tends to not do the hardest parts of those because they're not necessary to get the calculus. Calculus is the epitome of algebra, geometry, trigonometry, and pretty much that. You take those three and combine it with limits, and you have calculus.
Yes, sir.
What kind of matrix problem do you have?
First, we are dealing with some, well, I thought we were doing inverses, but maybe we're not. All right, determinants, more determinants.
Okay, hold on. My drawing pad went out, and it's back on. Okay, cool. See, matrices, you will not encounter those again until you take linear algebra, which is like a junior level mathematics course in college. Comes after Calc 1, Calc 2, and Calc 3. That's where you get linear algebra, and that's where matrices reappear.
Yes, sir. Okay. So, dealing with finding, okay. So, find the determinant of the matrix. Yes, finding the determinant of the matrix.
Huh?
So, it looks like it wants us to do this by minors. So let me give you the matrix.
Okay, again, I don't have minors, but I mean, I kind of do, but I did not refresh that skill because I just don't ever need it.
All right. I think I'll be able to pull up some notes if we have any questions.
Okay.
Maybe. All right. So the matrix is, and I'm going to go across the rows.
Okay.
It is a 4x4.
Okay.
0, B, 0, 0.
And there's no vertical line in the 3 columns, is there?
No, sir.
Okay, go ahead.
0, 0, C, 0. And maybe this one's simple, but it was odd. It looked odd, so I just wanted to. The next row is A, 0, 0, 0. And then the last row is 0, 0, 0, D.
Okay.
So remember, I think finding a matrix by its minors is the same thing as Let's do the minors of column 1. So remember what that does is we'll take A sub 1, 1, so row 1, column 1, the first 0 in the upper left-hand corner, and we will basically cancel out the row 1 and column. And then we find the determinant of that matrix which is left over.
That matrix right there?
That's right.
Okay. All right. That's easy enough to figure out, the determinant of that.
That's right.
What we do is add column 1 and column 2.
That's right.
And then we take that. What's that equal to?
0.
And
okay.
Add that.
0.
And we add that.
0. Wait, I think you multiply. Yeah, you multiply and you add the product. So D times 0 times C.
So far, everything's coming out to be 0. So it looks like the determinant of this 3 by 3 matrix. Oh no, it must be, yeah, it's going to be 0, isn't it?
Yes. That's okay. Yes. Okay, I see what it is. And even if you didn't, even if the determinant of the 3 by 3 wasn't 0, you'd still have to multiply it by the 0 of the A sub 1, 1.
In other words,
because when you're
0 up here.
Yes, sir.
Whatever that is, we multiply it. So the moment we know that, we know the answer is going to be 0, right? In other words, I really didn't have to go through all that stuff in blue.
Okay, that's
if I was going to multiply it by that A sub 1, 1, then I just know the answer is 0. So
that's right.
Now, what is that called? The A11 minors or something?
That would be the, yes, sir. That would be the A11 minor.
Okay, so let's do step 2. Again, you're directing, kind of.
All right, so that means, finding the determinant of a matrix by its minors, that basically means that we would do all of that for one row or one column. We have decided on column 1.
Okay.
But since it looks like they're all 0.
It looks like the next one's going to be that one, right?
0. Yes, sir.
In other words, I go across, and this minor,
it's going to be multiplied by 0 anyway.
Equals, no, it's going to be multiplied by B.
Oh, did I say column 1 or row 1?
I don't know. Which one is it supposed to be?
We can do either one. So we can do column. We can do row 1.
Let's do column B because it has a non-zero entry.
All right.
So we'll kind of see what this presents. So I know it's going to be 5 times the determinant of the rest of it. And we'll just say the determinant of the minor.
That's right.
Okay. Well, let's see. Let me write the 3 by 3 that results. AC0, A00, 0, and 0, 0D. Did I get that right?
I think the top left would be a 0, not an A.
Oh, I misread it. You're right. You're right.
I know I had that same thought.
Oh, yes. I see what I did. Yeah, okay. So let's see if we're going to produce anything but zeros here. Sorry, I have to kind of do it this way. This is the only way my mind remembers it. Looks like we have a DAC there. So something other than 0. Okay, so that's 0 plus
That's right.
0 plus
DAC.
So we'll write DAC minus, now we go the other way, that's 0.
Yes.
That's 0, and that's 0, correct?
Yes, sir. So it looks like
DAC. So DAC is the determinant. So B times DAC is, let's write it as ABCD.
ABCD.
Okay.
All right.
So that is the whatever. Is that correct terminology there?
I think it needs to be. Yes, that looks. I think it is. I mean, I don't know if you. I don't think you would write it out like that.
In other words, we're calculating the minors of everything exclusive of column 2 and row 1.
That's right.
Okay.
And I think that when you're finding, yes, that's right. When you're finding something by its minors, the minor of whatever element you are basically taking, we just took a sub 1, 2. If the subscripts, basically if they add up to an odd number, so 1 plus 2 is 3, that's an odd number, that means that the B would be negative. So it would be negative, A, B, C, D.
Oh.
Why that is, I don't know.
Okay.
But
I didn't know that. Good to know, yeah.
Basically the pattern basically goes by, if you had a matrix, the first row would go plus, minus, plus, minus, plus, minus. The second row would go minus, plus, minus, plus, minus. That would just repeat.
Okay. So let's see. It doesn't seem to make sense to do any of these zeros because we know what it's going to be.
That's right.
So the next one we probably should do is that one, right?
Oh, if we have to do it in all either one row or one column.
Oh.
So you
do all 4, and in other words, since we chose to do column 2, then the only other minors are column 3 and column 4. Is that right?
That's right.
Oh, okay. So this is the only answer we get. And what does that mean? Does that mean that's the determinant of this 4x4 matrix?
That means that is the determinant, yes.
Do you have answers on these?
Let me check.
Yeah, I can see if that's an answer.
If I can find the answer.
You kind of begin to see the value of this. If it lets you treat, 4x4s as basically the sum of 3x3s, which is you can figure out by the 2x2s. It's a little simpler than this system I have of drawing a 4th or a 5th and a 6th column. And I probably should have drawn a 7th column. I think I missed one. No, not if I'm doing the 3x3 determinant. Okay.
Okay, so the answer, as it turns out, is actually positive A, B, C, D.
Okay.
So I messed up somewhere with the negative. Where did I mess up with the negative?
You were saying if this was odd, it was negative, and if it's even, if the sum of that, 1 plus 2. So maybe it's the other way around?
That's right. Let me check that. I think, well, That's odd. I was right about the pattern. That would be a negative b, but that's strange. So it would be a negative b,
Okay.
but
Now, this one right here, if we were to start there, in other words, had we gone to a sub 3, 1 instead of what we went to, we're probably going to get an A, B, C, D again, or something similar. We'll get some positive number.
Oh, I think I know what we did.
Okay.
I think I know what we did.
Wow.
When we were finding the determinant of the minor, the matrix that we had was 0, C 0, A 0 0, and then 0 0.
So it was minus a B, C, D. Or an A, C, D.
That's right. It was a minus B, C, D.
And when you multiply by negative B, you get a positive. Oh, no.
That's right.
No, I'm sorry. Now I'm confused. I'm not sure I remember the rule here. But it's not important that I do as long as you do.
I think I know what it was. Okay. When we were finding the determinant
of this 3 by 3. Whoops.
Of that 3 by 3, yes, that's correct. We had basically we had how do I word this? When we had found the DAC, when we had found that term, we put it as a positive instead of a negative.
Yes, I remember.
That's basically what it was. We did it in the opposite order.
Okay. Oh, and this is an A right there. And that's how you get that. But why is that negative? That's in the first part of the determinant.
Multiplying sloping up like that, sloping up to the right, that's where you subtract. So sloping down to the right is where you add.
Oh, I did it wrong. In other words, I should have done that times that times that.
That's right.
Minus that times that times that. So that's where you get the minus DAC. You're absolutely right. That's the way. And the only way I remember it is this way. I know that is AD minus BC. Okay, so you start with down the negative slope, and then you subtract the positive slope.
That's right.
Yeah, okay. We done with this one?
That is all that one is.
Okay,
we're done
I just didn't want to erase it if we still had other stuff to talk about.
All right. This one should be more simple. This is a 2 by 2. We're still finding the determinant. Or maybe this isn't more simple. The first term is e raised to the 2x power. Yes. The next term is e to the 3x. Then there is 2e to the 2x. And then 3e to the 3x.
Yeah, and just treat it algebraically.
Okay, that's right.
So first thing you're going to do is multiply top left and bottom right. What does that equal?
Okay, so 3e to the 5x minus 2e to the 5x.
Which is equal to what?
That is equal to, is that right? 3e to the 5x?
Yeah. No, the other way. Did I write it wrong? Let's see. It's 3e minus 2e. Yeah.
That's right. E to the 5x.
Okay. In other words, that's 1e to the 5x. I got 3 of them minus 2 of them.
I don't know where I got 3 to the 5x from, but yes, that's right.
Okay. Yeah, you just, the common base is that, so you, excuse me, the common term, that's an apple. That's an apple. So you have 3 apples minus 2 apples.
That's right.
Which is equal to 1 apple. Okay?
For some reason, I thought it was like 5e to the 5x or something. All right, this one should be more interesting. It has trigonometric values.
Okay.
So it's another. Sir?
Is it a matrice still, or is it just trig?
It is a. Yes, sir. It's still a matrix.
I've never seen a matrix with trig functions in it.
So the first term is the sine of x.
Of course, I guess I've never seen a matrix with e in it either. So, okay.
The next term is the cosine of x.
This a 2 by 2?
2 by 2. Yes, sir.
Okay.
So the next term is the cosine of x again. And then the negative sine of x.
Okay, so the determinant of that thing is what?
So that's going to be negative sine squared x minus cosine squared x. So that's equal to -1, right?
Yeah. In other words, you factor out a negative, and you're left with sine squared x plus cosine squared x, and that's always 1.
Yes, sir.
Okay. Yeah.
Okay.
These aren't bad. These are actually easier, despite the fact that they're using exponentials and trig functions in place of numbers.
Yes, sir. Okay, let me see. So, 17, the matrix after introducing zeros. Okay, so this says that it wants us to find the determinant of the matrix after introducing zeros. Are you familiar with that?
I am.
Okay, so.
Maybe I am. Yeah, I think I do actually know what you're talking about. It's called row echelon.
I think so.
And there's another term for it too. And this is where you have the vertical line right there. Familiar with that?
I think so.
In other words, let's say, let me just kind of tell you what I remember. Let's say we have those two equations. We can set it up as a row echelon matrix. And this is what we do.
Yes, sir. That's right.
And then what we try to turn it into is something that looks like this. And what that tells you is that x is equal to that, and y is equal to that.
Yes, sir.
So this method, and what you've done is you've taken this matrix and turned it into this matrix by merely operating on it with, in other words, you can do anything that you want to these equations. You can multiply the second equation by 2, and it would be okay.
Right? Yes, sir.
And so what you do is you manipulate these rows of the matrix until it looks like 1, 0, and whatever number you get. And then you manipulate
Yes, sir.
the bottom, the next row, so that it looks like 0, 1, and whatever number you get. And by the
Yes,
time
sir.
you've manipulated the matrix so that it looks like that, you have your answer to the solution of those two systems of equations.
Yes, sir.
And this actually broke up into two different segments. I may have to look it up. There's row echelon, and then there's partial row echelon, where the second row doesn't end up. Let's say the second row ends up with something like this. Okay? In other words, it's not that easy to turn these things into 1, 0, and 0, 1. Well,
Yes, sir.
let's say I turn it into this matrix. Well, then I know what x is equal to. It's equal to that question mark. And once I know what x is equal to, it's easy enough to go back in, even to that row, and figure out what y is equal to.
Yes, sir.
So there's two levels of these row echelon. There's the super level, and I'm going to have to look in the book to figure out what the terminology is here, where you turn the whole matrix into 1, 0, 0, 1, and if it was a 3 by 3, you'd have a third row that was 0, 0, 1. Okay?
Yes, sir.
One thing that's unique to these matrices is this bar right there. You don't run into that in all matrices. That is strictly if you're trying to solve kind of a system of equations, and the easiest way it turns out to do it is to take this matrix and turn it into 1, 0, whatever, and 0, 1, whatever. Now, let me just suggest how I might do that from these two equations that I have. First of all, I can put them in whatever order, right, I want.
Yes, sir.
Well, that means I could rewrite this thing using that as equation 1, which gives me that 1 I'm looking for. And the second one would be 2, 3, 10. Now, I got to remember, I may need to, I got to refresh my, this is another one of those subjects that I get like once every 3 years. And
Yes,
if
sir.
I had a half hour to refresh, I'd know exactly how to do the second step. It is relatively
Yes, sir.
complicated.
Is it? Let me see if this sounds right to you, because maybe this is what I've heard. Let me see if this is the same thing.
Okay.
Would you be able to multiply a row or a column by something,
Yes.
and then add it?
And you can always add equations also. In other words, it operates pretty much on the same principles that solving simultaneous equations operates on. You can add the equations in either order you want, you can subtract them in either order you want, and you can multiply them by a constant on both sides.
Yes, sir.
And I think you're along the right track here.
So if we're trying,
remember how I turned that -4 into a 0. I would need to add it.
could you multiply column 1 by 4, add it to column 2, and put the answer in column 2? Is that right? Because I'm not sure if what I've heard is the same thing.
Rather than guessing, I would rather we tackle this at our next session, where I'll know exactly what to do. I've got 2 pages in my book that goes through exactly how to do these. Now, once you've done them manually once, you don't ever do them manually again, because your calculator actually has this function on it. In other words, you can put these row echelons into your calculator and it'll immediately solve that matrix so that it comes out 1, 0 number and 0, 1 number, which is your answer to your two equations, x and y.
Yes, sir.
But yeah, if you have other stuff we can work on for a half hour, I'd rather do it, and then I will review this and I'll know exactly what I'm talking about next time. Does that work?
Yes, sir. That works.
Okay. And anything like this, that's what I'd prefer to do. I don't mind working on a tough problem if I don't know how to do it, and both of us can kind of work on it and we get to the solution, and that's happened a couple of times, so that's fine. But in this particular case, I know exactly how to do it. I just got to refresh my brain by looking in the book.
Yes, sir.
And I don't think I can do it in real time by doing it that way. It might take me a half hour of refreshing.
Yes, sir. Okay. Let me make sure. Can you do some trig equations?
Yes. Great on trig equations. See, trig equations are taught to everybody. That's part of the Common Core. So any student I get, I got to do trig equations. But
yes, sir.
Matrices, you've gone to a level that I have never had any student go to in 10 years, doing the minors of the matrix.
Phew. Wow.
Now, I'm not sure what that means. It means either you have a teacher that really likes to touch the fringes, or I'm not sure what. But typically, you don't go from degree of difficulty 2 all the way up to 10 when you study geometry. You go up to maybe 7. 8, 9, and 10 are more for postdoc geometry students.
Wow.
Yeah, that's just the way math goes. And it's the same no matter what you're talking about. I could probably put up an algebra. No, I don't know about algebra. But certainly geometry, there are all kinds of problems that I would not be able to do in real time. And trig can get quite difficult also. But what do you got in trig? I'm pretty good in trig, especially solving equations. Having said that, watch, I won't be able to solve the first one, but go ahead.
Famous last words.
Yeah, really.
All right. 1 plus the cosine of x, all of that divided by 1 minus the cosine of x is equal to 0.
Okay. When you have a fraction equals to 0, what has to be true?
That means that the denominator is equal to 0.
Oh, it's the numerator.
The numerator.
Right.
You can't have the denominator 0 ever.
This can be 0 as if the numerator is 0.
That's right.
And I can multiply both sides by 1 minus cosine x. Now, the only thing we have to be a little bit careful of is that cannot be 0.
Yes, sir. That's right.
So we really have 2 equations to solve. We got to set that equal to 0. Let's do that. So cosine x equals -1. Did they give you a domain restriction for x, or is it all real numbers?
0 to 2 pi.
Okay, that's pretty typical. 0 to 2 pi. Okay, so where does that occur between 0 and 2 pi?
Pi. Is that right?
No. Remember here, there's a couple of ways to remember this, but the most important way is to remember the curve. Always be able to draw that curve with sine or cosine. And you'll notice there, excuse me, you're absolutely correct. I don't know what. I was thinking where it was equal to 0, and I was going to say there's 2 spots, but we're letting it equal to -1. Apologize.
Yes, sir.
You're absolutely correct. X has to be pi, and that's the only place.
Okay.
Now,
Good.
does that make our denominator 0?
So that means that the cosine of x is equal to 1, which means that x cannot be equal.
Well, let me suggest a different way of looking at it, Garrison. Just go ahead
Yes,
and
sir.
plug in pi for x and analyze what the denominator is equal to. If it's equal to anything but 0, we're fine. Doesn't really matter whether it's equal to 1 or 2 or 3 or a half, as long as it's not equal to 0. If it's equal to 0, we have problems, because then we're going to have 0 divided by 0, which isn't necessarily equal to 0.
Yes, sir.
But in this case, cosine of pi is 0, so the denominator is 1 minus 0. So it's equal to 1, we're fine.
Yes, sir.
So that's the only solution.
Yes, sir.
Okay, what else?
All right. So the cosine of x over 2 is equal to root 2 over 2.
Okay. So what is x? Also, the domain here is kind of critical. X goes from 0 to 2 pi again.
Yes, sir.
Okay. This gets a little tricky, but not that tricky. So x over 2 is equal to what? In other words, that's the angle.
X over 2 is equal to 90.
Well, the inverse cosine of what?
Oh, that's right. X over 2 is equal to the inverse cosine of root 2 over 2.
And what is that?
That is 45.
Okay. Do we leave it in degrees or should we put it in radians?
Radians. I think it's asking for radians. So that is
4.
pi over 4.
So that's what x over 2 is equal to. Where else? In the unit circle.
Oh, okay.
Let me do something else here. Let's look at it like this. Oops, hold on. This is kind of significant on these kind of problems. Right?
Yes, sir.
So where else? In that unit circle is x is the inverse cosine of root 2 over 2. In other words, we can't, even if we used a calculator, we wouldn't be able to count on that because we know there's 2 quadrants, right?
Yes, sir.
Yeah. Well, what's the other quadrant? Answer.
The fourth quadrant, so 7 pi over 4.
Okay. Now, that would appear to be x over 2. Those 2 answers. But
yes,
not
sir.
really, because the domain of x over 2 is not 0 to pi, or excuse me, 0 to 2 pi. X over 2's domain is 0 to pi. Which that is not an answer.
Okay.
Let me give you another problem that'll illustrate this perhaps a little bit better. And it's more typical. Where theta goes from 0 to 2 pi. And this will actually, I think, show it a lot better. So you solve for 2 theta. What's 2 theta equal to?
The inverse cosine of 3 pi over 2.
Or root 3 over.
Root 3 over 2. Root 3 over,
Okay.
sorry.
So 2 theta is equal to what?
That means that 2 theta is equal to 30 degrees.
Okay, which is pi over 6.
Pi over 6.
What else?
That is 150, which is 5 pi over 6.
No, it's got to be a 4th quadrant angle.
Oh, wait. Oh, yes, cosine. That's right. Okay. So that is, yes, 11 pi over 6.
Okay. Now, that would appear to be the answer, except you take it one step further and you divide everything by 2, so you get this. Correct?
Yes, sir.
Unfortunately, we've left off 2 valid answers because the domain of theta was 0 to 2 pi, which makes the domain of 2 theta 0 to 4 pi. So we have to do this all the way out to 4 pi. And I believe that's 13 pi over 6. And then I'm going to add 12 pi to this, so that's got to be 23 pi over 6. Okay? In other words, this is the unit circle, but I need 2 unit circles because I'm talking about 2 theta here. So I got to get that one also. And now when you go in and you divide all 4 answers by 2, you get all correct 4 answers.
Yes, sir.
And notice that all 4 answers are in the unit circle for theta, as they should be.
Yes, sir.
Every one of them is inside this original domain, which we have to have. But if you do this in a typical way, you would only end up with those 2 answers divided by 2, which means you'd only get these 2 answers. You would miss these 2 over here. So what really the first step is when you have these angles that are either multiplied or divided. First one was divided by 2. Second one's multiplied by 2. But if this said 4 theta, then I would have to figure out 4 theta would go from 0 to 8 pi.
That's right.
And I would have to figure out all of the answers going out to 8 pi for 4 theta, and then I'd divide each one of them by 4, and I would get 8 answers that were all inside the unit circle.
Yes, sir.
So that's the way these work when you have multiple angles inside the argument of the trig function. And
yes, sir.
These are far more typical than the one you gave me. In other words, it's much more common to run into this problem, 4 theta, than it is theta divided by 4. I almost never run into the other one. And probably because this is a little trickier. In other words, you don't have to know about expanding or diminishing your domain when it's theta over 2. You do have to know about it when it's 2 theta or 3 theta or 4 theta. If you don't expand that domain properly, you'll miss half of your answers. Whereas on the theta over 2, even if you come up with 2 answers like we did, it was easy enough to realize that the second answer was outside our domain.
Yes, sir.
All right, what else do you have in that area?
All right. Have cosine of x plus the sine of x times the tangent of x, the sine of x times the tangent of x, is equal to 2.
Okay. First thing first of all, let me say this. Trig functions are kind of notoriously difficult to solve if you've got different trig functions. Usually you want to get everything in terms of one trig function.
Yes, sir.
Right now we got 3. Is there anything I can do to reduce that?
So could we change the tangent into the sine of x over the cosine of x? What would you?
Yeah, exactly.
Okay.
Which now gives us cosine x plus sine squared x over cosine x equals 2. What's our next step?
We could multiply both sides by cosine of x, or?
Yeah, that's not a bad way to look at it. I prefer to look at it as adding those two fractions.
Okay.
Okay.
So we could do cosine of x, cosine squared of x plus sine squared of x, all of that over cosine x.
And the only reason I like looking at it that way is because once you get cosine squared plus sine squared, that always turns into a number 1.
That's right.
So now you have 1 over cosine x equals 2, right?
Yes, sir.
Okay, let me, hold on one second. Hold on. Sorry, my dog's having a seizure again, and she was right at the top of a long flight of stairs.
Oh.
So I had to move her away.
Okay.
There's no control over her body when she has one of these things. She would just fall down that flight of stairs and end up with a bag of bones at the bottom. So let's see. We had 1 over cosine x equals 2, which means cosine x equals what?
1/2.
And do we have a domain from 0 to 2 pi?
Yes, sir. 0 to 2 pi.
Where is x? Where's the cosine of x equal to 1/2?
That's going to be pi over 3, as well as 2 pi. Wait a minute. Not 2 pi over 3. That will be 5.
Yeah, let me tell you an easy way to figure it out. With cosine, start with 2 pi and subtract that. That gives you your second answer always. So it's 5 pi over 3.
5 pi over 3. Okay.
In other words, the angle 5 pi over 3, that's a negative pi over 3 angle, which is the same as this pi over 3 for cosine. In other words, cosine of minus pi over 3 is the same as the cosine of pi over 3. They're both positive, and they're both 1/2.
Yes, sir.
So there's your answer. And our domain stays between 0 and 2 pi here.
Yes, sir.
Okay. Now, we could have done it the way you suggested, where we multiply both sides by cosine. We still would have had cosine squared plus sine squared equals 2. Equals 2 cosine x. So it would have worked out the same way exactly.
Yes, sir.
It's just that my brain is geared towards looking for sine squared plus cosine squared.
Yes, sir. Okay. So now we have the secant of 4x is equal to 2. And this is within the same domain range. Yes, domain.
This first thing we should really do here.
Change that to cosine.
More with the domain. The domain we're really concerned about is that domain.
That's right.
So if we multiply in that domain by 4, we get
8 pi.
Yeah. So now when we solve for 4x, we solve for all 4x's up to 8 pi.
Yes, sir.
Okay. So we've got, we'll do what you suggested. That's 1 over cosine of 4x equals 2. Sir. So now we get, I'm going to switch them just for, right?
Yes, sir.
Okay, so what's 4x equal to?
The inverse cosine of 1/2, which is going to be 4x, is equal to pi over 3.
Okay. Now, give me the second one in the unit circle.
5 pi over 3.
Now give me the first one in the second unit circle. In other words, all you do is add 2 pi to that first one.
That's right. So that is 7 pi over 3.
And then just keep doing it until we got 8 answers. Or until we've gone out to 8 pi is what I should say.
All right. 7 pi over 3. And then we have, that is 11 pi over 3. 13 pi over 3.
That's 3 units. Oh, no, hold on. That's 1, 2, 3, 4. There's one more in there.
17 pi over 3.
And the last 2?
That is...
There's a pattern. Notice it goes 5, 7, 11, 13, 17. Next one must be 19.
That's right. 19 pi over 3.
And this one has to be 4 more, right?
23 pi over 3.
Okay. Now we're going to take each of those answers because those are the answers for 4x. We're trying to solve for x.
Yes, sir.
So what are the answers?
Pi over 12, 5 pi over 12, 7 pi over 12, okay. 11.
Let me just go ... 23 pi over 12. Notice that all 8 answers are in the unit circle. They're between 0 and 2 pi.
Yes, sir.
That's how you do those kind of problems. Is the very first thing you really want to do is figure out your domain of the argument.
Yes, sir.
All right. What else?
All right. So the cosecant squared of x is equal to 1 plus root 3, and that's in parentheses. So how would you say that? Would you say
yeah, the quantity 1 plus root 3, or left paren 1 plus root 3 right paren? Either of those?
All right. All right, equal to 1 plus root 3. So minus quantity 1 minus root 3 times the tangent of x.
And
wait,
that goes there, or is that tan x multiplying that whole quantity?
Just that 1 minus root 3. Cotan x.
Cotan x, okay. I was going to say, this looks like a situation where we're going to use that Pythagorean identity because we're dealing with a cosecant squared. Now, do I have it written correctly?
Let me check. Yes, sir.
In other words, this cotangent x is only multiplying the 1 minus root 3. It's not multiplying
Yes.
the 1 plus root 3?
Yes, sir. That's correct.
Okay. Okay. First of all, let's remember what our Pythagorean identity is for cosecant.
That is
let
cosecant is equal.
me give you an easier way to memorize it. This is the one that I don't ever have memorized, but as long as I know this one, I can figure out the other one.
Yes, sir.
So if I know that one, the cotangent squared of x plus 1 equals the cosecant squared of x. So I can always get this one by just using the cofunctions of that one.
Yes, sir.
Okay. And so cosecant squared of x is actually cotangent squared of x plus 1. So
yes, sir.
Let's substitute that in place of that so I don't have to. So that's cotangent squared of x plus 1. And now that's what we're dealing with.
Yes, sir.
All right.
All right.
This is a quadratic in disguise.
A quadratic in?
Yeah, in disguise. Let me give you another example of a quadratic in disguise. Just let's start with an easy one, and then we'll build up to a harder one.
Okay, that's right.
Okay. If I told you to solve that, that's a quadratic. And sine
Yes,
x is the way you refer to that. And it's also similar to something like this.
Yes, sir.
That's also a quadratic in e to the x. In other words, it's a quadratic in whatever that term is, the middle term. Most quadratics look like this. That would be a quadratic in x.
Yes, sir.
So the way, let me solve the simplest one here by factoring it. And you get sine x minus 2 times sine x plus 1. Okay? With me?
Yes, sir. Yes, sir.
Well, that can't be 0. Because that would mean that sine x is equal to 2, which it never is. Sines and cosines can only be between minus 1 and 1. So whenever you get one of your solutions that's impossible, in other words, this tells me that sine x minus 2 equals 0 or sine x plus 1 equals 0. One of those has to be true. Well, it's not that.
Yes, sir.
That's never equal to 0.
Yes, sir.
This one is. In other words, where x is 3 pi over 2, sine x is equal to minus 1. So that's our solution. And we started with this quadratic, which I call a quadratic in disguise, because most people don't necessarily think of that as a quadratic. But
yes, sir.
You can kind of see that that's what this problem we're dealing with is headed for. In other words, I have a cotangent squared term, I have a cotangent term, and I have a number. So let's treat it like a quadratic and put everything on one side. We're not going to have time necessarily to solve this, but I think you'll get the idea. I'm going to add that to both sides of the equation. So it's 1 minus root 3 times cotangent x. And all of that, and then I'm going to subtract this. So everything's on one side. Okay?
That's right.
There's your squared. There's your, this is a quadratic in cotangent x. And there's your constant.
Yes, sir.
So it looks like this. Ax squared plus bx plus c equals 0. Okay?
Yes.
Now, this is just strong enough or strange enough that maybe it's factorable, I don't know. But whether it's factorable or not, what can I use to solve it?
Quadratic formula.
Exactly. So x equals negative b, that's b, plus or minus b squared minus 4ac all over 2a. And a is 1, b is 1 minus root 3, and c is 1 plus root 3.
That's right.
So there's a lot of math or arithmetic you're going to have to do to come up with this answer, but that will solve, excuse me, I made one huge mistake. That's not what x is equal to, that's what the cotangent of x is equal to.
Okay, that's right.
Okay, because if this was a polynomial, that's what x would be equal to. But because it's a quadratic in cotangent x, then its cotangent x is equal to all of this.
Yes, sir.
And that will give you a number, and then you'll be able to take the inverse cotangent of that number to solve for x.
Yes, sir.
All right. They don't believe in giving you the easy ones, do they? Now,
I guess not.
It's possible that this may all magically disappear and this thing factors perfectly. I don't know. I'm not used to trying to factor things that have that as coefficients. But you can always use the quadratic, and that will give you the answer. So.
Yes, sir.
All right. Harrison, I'm going to let you go, and we'll talk again next Tuesday.
Yes, sir.
Okay, you have
See you then. You too.
Any